Welcome to Efiwe, Excellence Without Stress.
Welcome guys to Efiwe, Excellence Without Stress. And I remain your favorite chemistry tutor, Godson. About 60% of an average adult's body is made up of water. And 71% of the earth is also made up of that same water. This actually attests to the importance of water. So today, we are going to be looking into the concept of water. Now, water is regarded as the universal solvent. That is because it is a good solvent for most substances. And when we consider the different sources of water, we will notice that there are natural sources and treated sources. The natural sources we have are the rainwater, the well water, spring water, seawater, lake, and so many other natural bodies of water. When you now consider the treated water, we have distilled water, pipe-borne water, and chlorinated water. Let's now look into the structure of water. In a molecule of water, there are two elements, hydrogen and oxygen. But then these two elements, you'd have two atoms of hydrogen and one atom of oxygen. Oxygen in this particular structure is the central atom, and it has the configuration of 1s2, 2s2, and 2p4. This particular configuration implies that its valence shell will have two lone pairs of electrons and two unpaired electrons. Now, each of these unpaired electrons will now form a covalent bond with the electron from hydrogen atom. So that's why we're going to have two hydrogen atoms attaching themselves by a covalent bond to the two unpaired electrons. Now, the water molecule has two lone pairs and two bond pairs of electrons in its valence shell, and its central atom is oxygen. This automatically gives it an octet state, which brings about stability. This particular arrangement of water is what induces the shape of water as we would see. Ideally, the four electron pairs should be directly or directed towards corners of the tetrahedron, that is four sides. However, when the lone pairs of electrons are located near one another, these lone pairs induce a repulsion between them. This repulsion is so great that it squeezes the two bond pairs of electrons closer to each other. As a result, there is now a bond angle in water, compressed to approximately 105 degrees. Now, this particular compression leads to the structure of water being the V-shape. So as you can see, you will notice that the water looks like a V-shape. In some cases, you might have the structure said to be bent. So have that in mind, that the major reason this occurs is because the lone pairs of electrons are close to each other and they induce a repulsive force which squeezes the bond pair. Let's now look into the laboratory preparation of water. To prepare water in the lab, all you need to do is ignite dry hydrogen in air. So it's a spontaneous process that hydrogen bonds in air, and once it bonds in air, it reacts with oxygen to produce water. But it doesn't produce liquid water directly. What it gives is steam. Now, when this steam basically comes in contact with a cold surface, it then turns into liquid water. Now, the physical properties of water include water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. Secondly, the maximum density of water is 1 gram per cm cube at 4 degrees Celsius. This is basically going to be discussed in your physics with respect to your anomalous expansion of water. Water is also neutral to litmus, which means it is neither acidic nor alkaline. It is neutral. So, with that said, we are going to talk about the chemical properties of water. Water reacts with very electropositive metals to form an alkali and liberate hydrogen gas. So when sodium or potassium reacts with water, it tends to produce sodium hydroxide, potassium hydroxide, or calcium hydroxide and give off hydrogen gas. On the other hand, the lower metals like magnesium and zinc would react with only steam to still give off hydrogen gas and the oxide of the metal. Copper, gold, silver, and mercury do not react to water in any form. The second set of chemical reactions is that water tends to react with chlorine and most other halogens to form acidic solution. This particular acidic solution is going to be made up of a hydrohallic acid and a monooxohalate 1 acid. So in the case of chlorine, you have your hydrochloric acid and your monooxochlorate 1 acid. How then do we test to know if a substance is water? What do you simply do? Introduce the substance to a white anhydrous copper 2 sulfate salt and automatically, if it is water, it will turn blue. The indication or the conversion to the color of blue is as a result of the hydration of that salt. So basically, what happens is it hydrates the salt and changes the color. So if it is water, it will turn blue. If it is not water, it is not going to turn blue. Also, you can use blue cobalt 2 chloride, because that blue cobalt 2 chloride, when it is hydrated, will turn pink. Now note, these two tests are not specific for water. They only indicate the presence of water. That is to say, if you have an aqueous solution of sodium hydroxide and it comes in contact with these salts, automatically you are going to have, because of the aqueous solution contains water, it will have a positive test. So it's not like saying that anytime you see this thing, it means that only water is there. It's just trying to say that there is at least water there. It's not trying to indicate pure water. It's just trying to show the presence of water. Let's now go into the types of water. Water is of two types, namely soft water and hard water. Soft water forms lather easily with soap, hard water doesn't, basically. Hardness of water can actually be caused by dissolution of certain salts. Those salts include calcium sulfate, magnesium sulfate, or maybe your calcium bicarbonate, which is the calcium hydrogen trioxocarbonate 4. When it dissolves from the soil into the water, it tends to cause hardness of this water. Now, there are two types of hardness of water, and these types are dependent on what salts are dissolved. Temporal hardness is caused by the presence of calcium in the form of hydrogen trioxocarbonate 4. The implication is that once you have your calcium bicarbonate or calcium hydrogen trioxocarbonate 4 in the water in dissolved form, it tends to cause temporal hardness. The other form of hardness is permanent. We'll get to that. But then let's talk about how to remove temporal hardness. You have the physical method and the chemical method. Simply boil it for the physical method and you remove it. Why? Because when you heat bicarbonate salts, they tend to decompose to form insoluble carbonate salts and give off CO2. So the implication is this: when you are heating calcium bicarbonate, you break it down from the soluble form, which is the bicarbonate form, and then it forms the insoluble calcium carbonate. This calcium carbonate will now precipitate from the water, hence removing its hardness and making it soft. So that's that basically. So one easy method is to basically boil it. You simply convert it from the soluble form to its insoluble form. Let's continue. The next method is the chemical method. And by chemical method, you are going to be using your slaked lime. Your slaked lime is simply your calcium hydroxide solution. So the point is that it reacts with calcium bicarbonate to give calcium carbonate, which is insoluble, and it comes out of the water. So you either react it with your slaked lime or you happen to boil it, and automatically you are going to be removing the temporal hardness of water. What are the effects of removing temporal hardness, or the effects of having temporal hardness in your water? First of all is that it causes thawing of the kettles and boilers. You notice this whitey stuff that is formed when you use your boilers. Probably you don't use boilers, but when you use your kettles to boil hard water, automatically you have those white things that are formed. That's what we refer to as your thawing. The next one is your formation of stalagmites and stalactites in caves. So when you look at the stalactites, you are looking at a downward growing structure from the ceiling of the cave, while your stalagmite is basically growing from the cave floor. So in essence, this is basically what leads to the formation of some pillars in your cave, and that is as a result of the temporal hardness of water. Let's now talk about the permanent hardness of water. Permanent hardness in water is caused by the presence of calcium and magnesium ions in the form of soluble tetraoxosulfate 6 and their chlorides. So when you are considering the chlorides, or you are considering the sulfate salts of magnesium or calcium, automatically what you are looking into is the permanent hardness of water. How do we remove this permanent hardness? The first method is by using washing soda. Now, washing soda is your sodium trioxocarbonate 4, and when it reacts with your calcium sulfate, it tends to precipitate the calcium from it. Remember, the emphasis is the calcium ion and the magnesium ion. So once the calcium ion becomes insoluble, automatically it removes the hardness. So as you can see in this reaction, when sodium carbonate reacts with calcium sulfate, there is more like a double decomposition, and then you have that calcium carbonate will now leave the solution because calcium carbonate is insoluble. Hence, even if sodium sulfate is there, it doesn't cause hardness. So you find out that once you remove the calcium ion by making it insoluble, you have removed the hardness. The second method is by using caustic soda. Caustic soda is sodium hydroxide. If it reacts, the same principle also applies, and then it removes it. Also, you could use your sodium zeolite. If you do that too, you are also going to remove calcium ion or magnesium ion from the solution. And hence, you have removed the permanent hardness of water. What then is the advantage of hardness of water? First of all is that the salt would make it to have a better taste than soft water. Yes. And then calcium salts in it helps to build strong teeth and bones. So it's important that you take hard forms of water. You get. It provides calcium carbonate. The crabs and the snails used to build their shells. It does not dissolve lead. Yes, one of the disadvantages of soft water is that it tends to dissolve lead. And when it dissolves lead, it becomes poisonous because it leads to lead poisoning. And when you take it in, automatically you have some health issues. So hard water does not dissolve lead pipes. We now go into the disadvantages. Yes, it falls your kettles and makes it hard to wash, makes your kettles and your boilers a little bit messy. It wastes a lot of soap because, as we know, hard water is hard to form ladder. Okay, so for those of us that have wells in our areas, when you use well water to wash, you notice that you will need to put a lot of detergent for it to form ladders. And then finally, it cannot be used in dyeing and tanning because it tends to interact with the dyes. So we would go to the next part of our study of water, and that is the treatment of water for town supply. The following are the things you need to do to river water or any other sources of water for you to make it usable for people to get it in their towns, basically. So first of all, coagulation. Chemicals like potash alum or sodium aluminate is added to the water in large settling tanks. And what it does is that it pulls those dirts, the dust, and everything together. That is coagulation. Now, after the particles have been coagulated, the next thing that happens is sedimentation. This particular tank is allowed to stay for a little while such that those coagulated particles will now settle to the bottom of the tank. That is sedimentation. Then we now go into filtration. The water above the sediment still contains some suspended particles. So this water is passed through a filter bed to remove the remaining fine dirt. So that is that. And then we begin to introduce our chemicals. The first one we do is chlorination. The reason you introduce a chemical like chlorine is so that it will kill germs. Iodine and fluorine are basically added as food supplements to prevent goiter and tooth decay. That is to say, iodine prevents goiter while fluorine prevents tooth decay, respectively, as we can see. The treated water is then stored in reservoirs and eventually it is distributed to the town. So that is that about your treatment of water for town supply. As you can see, you could see a diagram to describe this. You have your rainwater pushed into where it is coagulated. You have the flocculation, sedimentation, pass through a filter bed, and hence you have your disinfection and addition of your chemicals. And then from there, it is passed into our different homes. As we know, water is known as a universal solvent, as it dissolves all polar substances. Atmospheric gases can be dissolved in water too. The ocean can also dissolve gases that are very important to living organisms, particularly oxygen and carbon dioxide, and also nitrogen. When CO2 is dissolved in water, it tends to make it more acidic because of the formation of your carbonic acid. So that's important that you take note of. Now, we are going to get into the discussion of water of crystallization, fluorescence, deliquescence, and hygroscopy. Water of crystallization is simply the number of water molecules that is combined chemically in definite molecular proportions with concerned salts in crystalline state. The water is responsible for the geometric shape and color of the crystal. So you will notice that if you add 5 water molecules to your copper sulfate, it tends to change the color from white to blue. Same thing applies to cobalt 2 chloride where it changes to pink. So hydration, when you add water molecules in specific proportion to the chemical formula of a particular compound, that particular water attached is what we refer to as the water of crystallization. Then we go into the next one, which is an efflorescent substance. Efflorescent substances are basically substances that remove water. When they remove water as a result of exposure to the atmosphere, they are referred to as efflorescents. And when they remove this water, they become powdery. basically, instead of crystalline. So once a particular substance has the ability to remove its water of crystallization as a result of exposure to the air, it is said to be a fluorescent. On the other hand, a deliquescent substance is a substance that absorbs water from the atmosphere and becomes dissolved to form a solution. So once a substance collects water from the atmosphere, or when it is exposed to air to form a solution, it is said to become, or it is referred to as, a deliquescent substance. Hygroscopic substances are just like deliquescent substance, but the difference is that they do not form solutions. So hygroscopy is the ability of a substance to attract and hold water molecules from surrounding environment. This is often exhibited by substance ability to dissolve in water. However, as I said, the difference between hygroscopic and deliquescent substance is that the hygroscopic substance does not, in most cases, form solutions, but the deliquescent substance would form solutions. Hygroscopic substances tend to have a high affinity for water, which allows them to absorb moisture from the air. This can be beneficial for substances that are used in humid environments, as it helps to keep them moist. However, it can also be a disadvantage for some substances that are used in dry environments, as it can lead to them becoming damp and unstable. So, what are drying agents? What we use majorly as our drying agents are our deliquescent and hygroscopic substances. This is because they tend to collect water from the atmosphere. So they have a high affinity for water, so they attract water molecules from their environment. Some products such as paints, adhesive, and solvents contain volatile organic compounds that can give off harmful fumes. A drying agent is a substance that helps to speed up the evaporation of these harmful compounds. Drying agents work by absorbing the liquid component of the fume. So when they take the water from those fumes, automatically it vaporizes them. This allows the fumes to dissipate more quickly, reducing the risk of exposure. So we are looking at how a drying agent can be advantageous. One common drying agent is fused calcium chloride. It is white, it is crystalline, and is used in a variety of applications, including dehumidifiers and as a desiccant. Other drying agents include activated carbon and silica gel. So we'll look at the list of drying agents and their common gases they dry. Conc H2SO4 dries all gases except ammonia. This is not ammonium, it's a typographical error. This should be ammonia and hydrogen sulfide. Fused calcium chloride, all gases also except ammonia. The reason Conc H2SO4 does not dry ammonia is because it tends to react with ammonia. Ammonia is base, Conc H2SO4 is an acid, and when they react, automatically it's neutralization reaction that will occur. On the other hand, for hydrogen sulfide, you would have that there would be a redox process that would occur because the hydrogen sulfide is a strong reducing agent and would react with Conc H2SO4, which is a strong oxidizing agent. So basically, redox will occur with hydrogen sulfide, while neutralization will occur with ammonia. Please note that is not ammonium, that's ammonia. Then you cannot use fused calcium chloride to dry ammonia simply because it will form a complex with the fused calcium chloride. Okay, phosphorus 5 oxide can be used to dry all gases except ammonia. Same thing because ammonia reacts with phosphorus 5 oxide. And then you have quicklime. Quicklime is used to dry ammonia, yes, because it doesn't react or interact with it. Silica gel can be used to dry all gases, including ammonia. With that said, substances that exhibit efflorescence are mostly salts with water of crystallization. So you know that it has to lose water. The implication is that if it doesn't have the water to lose, it would definitely not be referred to as efflorescence. So example is your global salt, which is your sodium tetraoxosulfate 6 decahydrate. So once it loses its water of crystallization, it is said to be efflorescence as a result of exposure to air. Substances that absorb water from the atmosphere and form solutions are deliquescent, and the examples of those substances include calcium chloride, sodium hydroxide, potassium hydroxide, magnesium chloride, phosphorus 5 oxide, iron 3 chloride, and other examples not mentioned here. Hygroscopic substances do not turn into solutions when they absorb water from the atmosphere, as I have always mentioned. And the examples of these substances include calcium oxide, sodium triazonitrate 5, copper 2 oxide, and your Conc H2SO4. With this, we have come to the end of this study. And I hope you've seen how important water is, how to test water, and the different interactions of water with other substances. Thank you very much for studying with us. Hi guys, this is Efiwe, Excellence Without Stress, and I am your favorite chemistry tutor, Godson. Did you guys know that some solutions are true while others are false? For instance, air is a true solution, but smoke is a false solution. Sugar in water is a true solution, but blood is a false solution. Join me as we go through the concept of types of mixtures, where we would understand true solutions, colloids, and suspensions. Let's get into it. Now, a mixture is simply a combination of two or more substances that are not chemically bound together. And this implies that the constituents can be separated by physical processes. On the basis of this, there are three major types of mixtures, and they include true solutions, colloidal solutions, or false solutions. That's the other name for colloidal solutions. And then you have your suspension. Now let's understand what these things actually mean. What is a true solution? A true solution is a homogeneous mixture of two or more substances. The implication is that the emphasis in true solution is the term homogeneous. Once you are looking at homogeneous, it implies that you cannot differentiate between the two substances. When you look at this, it looks exactly like it's just one. The other implication or way of describing it is that this is a solution that is just in one phase. You have a solution in one phase as a solution that you cannot differentiate between the solute and the solvent. That is to say, both things are mixed homogeneously. Consider air, for instance. If you look at air is a mixture of nitrogen, oxygen, your rare gases, and the rest of them, including water vapor. But you notice that looking at air, you can't differentiate between these particles, hence the term homogeneous. So air is homogeneous, sugar and salt solutions are homogeneous, beer, your soda drink, salt, all these things are true solutions. Why? Because they are homogeneous mixtures of two or more substances. A colloid, on the other hand, is a mixture in which one substance consisting of microscopical dispersed insoluble particle is suspended throughout another substance. The point is this: in colloids, the solutions are not necessarily, will I say, homogeneous. But the thing is that particles that are dissolved are very, very microscopic, and you can't see them with your eyes. However, it does not mean that they are dissolved. So the difference between a false solution and a true solution is that in a true solution, the substances are dissolved, but in a false solution, the substances are not dissolved. They are simply dispersed. Blood, for instance, is made up of water and blood cells. The blood cells are not dissolved in water, they are simply dispersed. And because they are microscopic, you will not be able to see them with your physical eye, but it doesn't mean that the cells are dissolved. So have that in mind. Now, once it is simply dispersed, it is referred to as a colloidal solution. But if it is dissolved completely, you are talking about a true solution. So, it is made up of two phases. As I mentioned, in true solution, just one phase, but in this case, two phases: dispersed substances and the medium of dispersal. So if I have the blood cells are the dispersed substances, while the medium of dispersal is the plasma, which is made up of 90% plus of water. So, moving ahead, it is more like an intermediate between the true solution and suspension because it possesses some properties of true solutions and some properties of suspension. So that is to say, a colloid is not entirely, it doesn't have all the properties of true solutions, and it doesn't have all the properties of suspension. It just picks one from here, or some from here, hence making it an intermediate mixture. What are the types of colloids? You have the salts and gels, and when you talk about salts and gels, you are looking at solid dispersed in liquid colloid. A gel is a solidified salt. Now, gels can also be considered as colloids in which solids exceeds liquids. We're going to be looking at examples to help us buttress this. So, as I said earlier on, I will just list this and then we go to the table to consider the examples properly. Aerosols are when solids and liquids are dispersed in gas, like smoke. Solid particles dispersed in gas, that's an aerosol. When you have your sprays from your aerosol cans, that is also an aerosol because when you spray the liquids inside the gas, which is air, you form an aerosol. Foam is simply gas in liquid. That is when you're talking about your soap ladder, that's the type of foam you're talking about. But when you consider your solid foam is basically what is used in making our mattresses, you get, and that is when gas is dispersed in solid. Then you have your emulsion, which is your liquid in liquid. So let's consider these things with the examples. Now, as I said, the dispersed substance is the particle that you disperse. Then the medium of dispersal is that particular substance that carries the dispersed substance. So if you have blood and you have your plasma, the blood cells are particles that are dispersed inside the plasma, which is the liquid that carries them. Now the point about it is that it is not always a liquid, it could be gas, it could be solid. But just have that in mind, that in every colloid you have the dispersed substance and the medium of dispersal. So let's consider this now. If, for instance, we have a gas as the dispersed substance and it is dispersed in another gas, there is no such colloids. So just know that there is no colloid that has gas dispersed in gas. On the other hand, if a liquid is dispersed in gas, it forms liquid aerosols. So that is to say, when you disperse a liquid inside gas, example is your fog, your mist, your steam, your sprays, any spray from an aerosol can, you happen to spray your, what we call perfume, you get. So when you spray it, automatically it comes out of the aerosol cans as liquids dispersed in gas. What it forms is not a solution, it forms a liquid aerosol. Now, if a solid, on the other hand, is now dispersed in gas, it forms a solid aerosol. In this case, we have smoke, your ice cold, your atmospheric particulate matter, and the rest of them. So once solid is dispersed in gas, that is your solid aerosol. So smoke is an example of solid aerosol. Okay, moving down, we have that if a gas, as you can see, is now dispersed in a liquid, what is this going to be referred to as? Foam. But this foam is more or less your liquid foam. So situations where you have your whipped cream, your shaving cream, other places where you have your soap ladder too, and the bubbles, these are basically when gases are dispersed in liquid, and what they form is a phase or a particular colloid known as the foam. On the other hand, if a liquid is now dispersed in another liquid, it forms an emulsion or liquid crystal. The emulsion examples include your milk, your mayonnaise, your hand cream, your latex, your biological membranes, your hair cream, and the rest of them. Why? Because in the production of these substances, liquids are combined with liquids, and they do not form through solutions, they form colloids. The type of colloids that are formed when liquids combine with liquids are emulsions. Okay, now what if a solid decides to be dispersed in a liquid? When a solid is dispersed in a liquid, the type of emulsion formed is called sol. So, as I mentioned earlier, if you look at the earlier slide, we said salts and gels. Solid in liquid is salts. Aerosol, solid and liquid in gas. Foam is gas in liquid. Solid foam, gas in solid. Emulsion, liquid in liquid, as we have been seeing. So, considering the examples of salts, you have your pigmented ink, your sediments, the agar, that's your biomolecular condensates. You have your gum, the blood that I mentioned earlier on. The blood is a dispersion of solid particles, which are the cells, which are dispersed in liquid, which is the plasma. So have that in mind, that your blood is also a sol. Okay, now what if we now have a different scenario where gases are dispersed in solid? If a gas is dispersed in the solid, the type of colloid it forms is called the solid foam, where you have your aerogel, your floating soap, styrofoam. Styrofoam is basically those white stuff. If you buy a new television in Nigeria, in your Nigerian home, those white stuff that are used to kind of pack the TV to prevent it from breaking, or any other thing you buy usually in your washing machines, or most of those white stuff they used to pack it to hold them together, that we now use and cut. Some of us cut it into guns. Anyway, that's not what we're talking about. Those guys are your styrofoam. And how are they formed? By dispersal of gas in solid. The type of colloid that they are referred to as is your solid form. Okay, now if a liquid is now dispersed in a solid, it is called gel. If you notice, when a solid was dispersed in liquid, it is called sol. But if a liquid is now dispersed in a solid, it is called gel. One other thing you can use or interrelate them with is that sols and gels. A sol is a liquid gel, while gel is a solid sol. You get, because whenever a sol solidifies, what it forms is gelatinous, and that is the gel. But let's continue. Now you have your agar, gelatin. You have your jelly or jelly-like biomolecular condensates. Those guys are classified as gel. And then we have the final one, which is solid in solid. Solid in solids are referred to as solid salts. A very good example is your cranberry glass. So when you disperse a solid inside another solid, what you have is your solid salt. So basically, that is that about the examples of your different colloidal mixtures. We go into the next one, suspension. A suspension is straight up a heterozygous mixture of two or more substances. So once you are combining two or more substances and there is no homogeneity, it is a suspension. So if you are making soup, yes, our beautiful ofe egusi, as we all call it in the East, or the egusi soup as we all know, or your okra or your ora, any form of soup, the meat cannot combine with the water and form a homogeneous mixture. It's not possible. It will always remain heterogeneous. So the point about it is, once you combine anything and it is heterogeneous, you have that it is referred to as a suspension instead of a solution. So when you pour your chocolate inside water and it doesn't dissolve, what you have there is not a solution, it is simply a suspension. Okay, now with that said, we are going to be looking at the comparative properties of the types of mixtures, and then with this we'll consider their differences. Take for instance, you have the first one, property, particle size. Suspensions are greater than 100 nanometers. Colloids are about 1 to 100 nanometers. Then you have that particles of true solutions have diameters of less than 1 nanometer. So have that in mind, that with respect to size, the smallest is solution, the largest is suspension. Now, because of this size, the implication is that when you pass these three mixtures through a filter paper, it is possible to filter suspensions because their size are larger than the holes of a filter paper. Unlike in the case of your colloidal solutions, which have small size as well as your solution. So, true solutions and colloids cannot be filtered, but suspensions can be filtered. We go to the next one, sedimentation or settling. Yes, colloidal particles, let's start with suspension. Suspensions settle on their own. If you have this mixture of mud water, for instance, or some of us that use well water, in dry season, you'll notice that the well water is usually dirty, and then you just fetch it like that and keep it, and after a while, the particles settles. It's because the mixture is a suspension. So once you keep a particular chalk in water, for instance, chalk in water, you'll notice that where most of us that went to government primary schools in Nigeria, when we mix chalk with water to play around in our primary schools back in the day, or in secondary schools, you'll notice that the chalk, after you mix it with water, will eventually settle if you keep it for a while. Why is that happening? Because chalk in water is a suspension, so suspensions settle. The egusi soup I was talking about too, the large chunks of meat and every other thing that is put, if you keep the soup after a while, it tends to settle. So have that in mind, that once you keep a mixture and you notice that particles of the mixture settle to the base or sediment, the implication is that what you have as that mixture is a suspension. Colloidal solutions only settle after centrifugation. That is when you spin it at a very high speed in a centrifuge. That is the only time they settle. However, solutions do not settle under any condition. So that's that basically. Appearance. When you consider a suspension, it is usually opaque. Yes, in most cases, it doesn't allow the passage of light. Your colloidal solutions can be transparent. In some cases, they can be translucent, which means some of the colloidal solutions will not allow light to pass through them completely, while some of them will allow light. True solutions are completely transparent, which means they allow light to pass through them. And one of the reasons they allow light is because their particles are too small, so they can't prevent the rays of light from passing through. Unlike in the case of suspensions, because their particles are large, they tend to distort the direction of light. And in some cases, they just block it completely. That's why they are referred to as opaque. Then we go to Tyndall effect. Now, Tyndall effect is the scattering of light rays by particles of a mixture. And you will notice that if you pass a light ray through a true solution, you will not see the light ray. But if it is passing through a colloid or a suspension, you are likely to see the visible light rays. Why is that? The particles of this particular colloid and suspension have distorted the direction of the light rays, hence making it to become visible. So when you are considering Tyndall effect, it is simply the scattering of light rays by particles of a mixture. To illustrate this, we could just probably look into, consider this for instance. Let's say you have, your light rays moving in a particular direction, and if you have a true solution, because the particles of true solutions are very infinitesimal, these light rays will pass without any obstruction. You get? Now, but in the case of your colloidal mixtures, the particles are relatively larger. Hence, when they hit the light, when the light ray hits them, because the light rays have the wave-particle duality, they are considered as particles too, their direction can be distorted. And that is basically what leads to Tyndall effect. In the case of your most large particles, which are those of the suspension, obviously it either blocks it entirely or then distorts the direction. Hence, through solutions, it goes through straight without any obstruction. For solutions of colloids, there will be a distortion, which implies Tyndall effect. Also, in the case of suspensions, distortion, which also describes Tyndall effect. So you have that. Whenever we are trying to discuss your true solutions, there will be no Tyndall effect. As you can see, the light beam is not visible. You have that here. But once it passes through a colloid, milk for instance, which is an emulsion, you begin to see the light because of the distortion. Also applies to your suspension. With this said, we go back to continue. Now, the next thing is diffusion of particles. Suspensions do not diffuse. Colloids diffuse slowly, or solutions diffuse rapidly. If you now consider your Brownian motion, Brownian motion may show in suspensions. It shows definitely in your colloidal solution, but may or may not show in true solutions. Nature. Suspensions are always heterogeneous. Colloidal solutions also are heterogeneous, while true solutions are always homogeneous. With this, we have come to the end of this study. I hope you've learned a lot about solutions. Thank you very much. Don't forget to solve questions on the Efiwe app, and if you don't have it, do download them. Welcome guys to Efiwe, Excellence Without Stress. And I remain your favorite chemistry tutor, Godson. Now, how many of you have noticed that when making your chocolate drink, yes, your chocolate drink, not tea, that one with the mix Milo and milk, that one, you notice that the chocolate dissolves faster in hot water than in cold water? Or have you also noticed that when making that sweet egusi soup, my God, that the oil would seem to dissolve once it starts boiling? When you pour the oil initially, it will not start dissolving, but after a while as it boils, what happens? It begins to dissolve. So, what exactly is the reason this is happening? Join me on this journey to understand the concept of solubility. Now, in this study, we are going to be sharing or discussing them in different parts. Introduction to solubility, factors that affect solubility, solubility formulas, amount of crystals and water of crystallization, understanding solubility curve, and finally, solubility products. Let's get into the study. Solubility is simply a measure of how soluble a substance is in a solvent. That is to say, for instance, sugar dissolves more in water than our akam. You know, your pap, your custard, the rest of them. Those ones don't dissolve as much as sugar. So what is that telling you? The amount of sugar that will dissolve in the quantity of water might not be the same thing as the amount of pap or dawa or custard that will dissolve in water. When we are simply measuring these things, how soluble a substance is, what we are considering is solubility. So by definition, it is the maximum amount of solute that can be dissolved in a given amount of solvent at a particular temperature. If you notice the highlighted words, maximum amount and particular temperature, I will tell you why maximum amount was highlighted. Generally speaking, concentration is simply the amount of solute in a solvent. So anytime you're thinking about concentration, you're just considering the amount of solute in a solvent. However, when that amount is maximum, that concentration is not just any concentration, it is now solubility. So the implication is that I can actually say that solubility is the maximum concentration of a substance at a particular temperature. So have that in mind, that the emphasized terminology here is maximum amount of solute that is dissolved in a given amount of solvent. Now, also notice that I highlighted particular temperature. Other words you can use in place of particular temperature is given temperature or specific temperature. Please don't use constant, don't use same. What you're supposed to use is given or specific. This is just trying to say that if you change the temperature, the solubility is likely to change, as we will see ahead. Now, it is important to note that a solution is made up of a solute and a solvent. A solute is the dissolved substance, while the solvent is the substance that dissolves. So if I have sugar and water, because I'm going to dissolve the sugar inside water, the sugar is going to be referred to as the solute, while the solvent is the water. And basically that. Okay. Now, what are the important things that should be noted? It's important to note that every solution can generally be classified as unsaturated. An unsaturated solution is a solution that can still dissolve more solutes at a particular temperature. Yes. So if it can still take in more solutes, it is referred to as unsaturated. A good illustration to help us understand this is if we happen to consider, let's say we consider a particular cup of water. And if I tell you that the maximum amount of sugar or substance that can enter this cup is 5 grams. However, instead of putting 5 grams, I introduced 3 grams. Notice something, that this particular cup can still take in how many more? 2 grams, which means in this case, it is unsaturated. So when a solution can still accept more solute or dissolve more solute at a given temperature, then that particular solution is said to be unsaturated. Okay, moving ahead. The next type of solution we are considering here is a saturated solution. A saturated solution is a solution that can no longer dissolve more solutes, even in the presence of undissolved solutes at a particular temperature. What this means is that the fact that it is not dissolving is not because there are no more solutes. It is simply because of the fact that it is filled. So, if I have, for instance, that this solution can take 5, and then 5 has entered, automatically this solution is said to be saturated. Now, even if I bring 100 more, you will notice that that 100 will stay outside, it can't enter, and that is why this is referred to as a saturated solution. Finally, we have a supersaturated solution. As I said, the maximum that can enter is 5, but in a situation when you now put more than 5, let's say you introduce, as we see here, 105, or maybe you introduce 10. If you introduce 10, 5 grams will enter, 5 grams will stay out. This is because you introduced 10 grams. Now, this solution is now said to be supersaturated. Why? It has more than what it would take to saturate it. So if you look at what we just said, a supersaturated solution is a solution that has much more solutes than that found in a saturated solution at a particular temperature. With these definitions in mind, solubility can then be described as the concentration of a saturated solution, because the saturated solution is filled. The highest amount that can enter it has gotten into it. So when you consider the concentration of a saturated solution, that is solubility. So just have that in mind, that once you see questions and they're asking questions with respect to saturated solution, the implication is that there is a relationship between that particular solution and solubility. Let's move ahead. Now we're going to be considering the factors that affect solubility. Yes, there are certain things that you will do to increase solubility of a substance and certain things that you will do to decrease the solubility of a substance. The first one is the nature of the solute and solvent. Yes. Generally speaking, polar solutes are dissolved most effectively in polar solvents, while non-polar solutes are dissolved most effectively in non-polar solvents. It's for a very good example or a very good illustration is a situation where you have a drop of oil staining your cloth. You will notice that using water to try to clean away that drop of oil will not work. Why? Oil is non-polar, but water is polar. Hence, oil which is non-polar will not effectively be dissolved by water which is polar. If you want to get that stain out, you could use kerosene. And as you resolve the non-polar oil in non-polar kerosene, it tends to move away. So have that in mind, that when you want to effectively dissolve a polar substance, use a polar solvent. If you want to dissolve a non-polar substance, use a non-polar solvent. Moving ahead. Pressure. Pressure does not affect the solubility of solids and liquids. Take note of this. The only state of matter that pressure change could affect is that of gases. And how does it affect it? if you increase the pressure, you are increasing the solubility. How I usually see it in my mind is that you are pressing the gases into the solution. You know, pressure is like applying, you say apply pressure, like pressing the gas. So basically that. So when you are pressing the gas, you are forcing them into the solution, and as you are forcing them in, more of the gases will tend to dissolve inside the solution. So that's that. If you consider a Coke bottle, for instance, I like using this illustration. So if you consider a Coke bottle, you will notice that, let's take this all out. You will notice that for a Coke bottle, let's say, or any other soda drink, any other fizzy drink, this is my Coke. Wow, so much for drawing Coke. Let's try another way. Okay, so let's say, yes, maybe this is not like the original Coke. Okay, so you will notice that there's a little space given here, then the drink is here. Let me not, let's say this is Coke, because this is not the actual Coca-Cola. Okay, so you have the drink here, and then there's this little space here. Now, the principle here is small volume. And we notice that when you leave a little volume, automatically because of Boyle's law, there will be high pressure. Now, the presence of this high pressure tends to push carbon dioxide gas into the drink. CO2 is normally non-polar. And the major solvent in your fizzy drinks is water. So how then do we dissolve a non-polar substance in a polar substance? Because of the fact that increasing pressure increases the solubility of gases. As this small volume exists, it causes a high pressure, hence dissolving the CO2 gas in the drink. Notice something. Once you open this drink, you will just hear that sound, and then effervescence occurs, and then the CO2 leaves. If you leave that particular Coke bottle open over time, you will notice that that drink will no more give you that refreshing taste. Why? Because what gives the refreshing taste is your CO2. So if you don't have that taste, it is simply because the CO2 has completely gone out. So basically, that's that. So you have that. If you are considering your gases, if you increase the pressure, you tend to increase the solubility. And one of the applications is in dissolution of gases in your fizzy drinks. Okay, having said that, we continue to the next one, and that is temperature. Now, temperature has a tendency to affect the solubility, and the general tendency is this: an increase in temperature generally increases the solubility of most solids, but on the other hand, it decreases the solubility of most gases. So when you are increasing temperature, you are increasing solubility of solids and liquids. However, when you are increasing temperature, the solubility of gases will be reducing. Of most gases, not every gas though, most gases. I think HCl gas is an exception to this. So take note of that. That most gases would decrease in solubility once you are increasing temperature, and increase in solubility once you are decreasing temperature. Now, the effect of this increase in temperature on solubility is dependent on the solid, on if the solid dissolves endothermically or probably exothermically. If the solution is endothermic, it is favored by an increase in temperature. If the solution is exothermic, it is favored by a decrease in temperature. But you will notice something. Most of the solids, when they dissolve endothermically. That is why I said that most solids have an increase in solubility once there's an increase in temperature. So take note of that. Now, the next point, which we are going to get into, is common ion effect. Now, common ion effect basically describes how impurities affect solubility. Generally speaking, impurities or the presence of impurities in solvents do not affect the solubility of other solids, except in a situation where there are similar ions between the impurity and the solute. Before we come to this, let's look at an illustration. If, for instance, I walk into a class with my girlfriend, I don't know why I like using this illustration, but yeah, I walk into a class with my girlfriend, and we're just together talking, chatting, and then some guys come in. If I go to greet the guys, you will notice that there will be no problem. But once a girl comes in and I try to, say hi to her, my jealous girlfriend might have an issue with that girl. Why? The both of them are similar. She sees her as a competition. So what does this mean? It means that if the impurity does not have the same thing as the solute, automatically no problem. You can come in as much as you want. But once there is a similarity, they begin to repel each other. That's how I see it. So if we are to look at our screen, so you could have a condition or a situation where, let's say HCl, This is water, but then HCl is an impurity. Now, where HCl is an impurity, if I decide to introduce something like your calcium sulfate, notice this, that there is no similar ion. The cations, not similar. And therefore, you find out that there is no problem. It would not affect it. You can come in. Check for the anions. The anions, not similar. So which means there will be no problem. You can come in. Hence, solubility is not affected. It doesn't increase the solubility. It doesn't decrease it. It just doesn't affect it. It allows it in as it should when it is just water. Now, but in a situation or a condition where, for instance, I have hydrochloric acid or HCl as an impurity inside water, and I am trying to dissolve NaCl. Notice something. The cations, not similar. So no problem here. But when you consider the anions, you will notice that Cl and Cl, similar. And once the ions are similar between the impurity and the solute, automatically it means that it will reduce the solubility of the solute. Now, this principle is majorly applied in your saponification process, and the process is known as salting out, where you introduce your sodium chloride salt to reduce the solubility of the soap and then salt out the soap from its mixture with glycerol. So have that in mind. An application of common ion effects is in soap making, and what is basically used is the salt, NaCl, and the process is referred to as salting out. Okay, so having said that, we have come to the end of the factors affecting solubility. Let's simply try out one question to understand or buttress our understanding. Which of the following statements is correct? Option A, okay, the solubility of dash, option A, gases increase with an increase in temperature. Nah, that's so wrong. Because we have that if temperature increases, it decreases the solubility of gases. So yes, option A is wrong. Option B, gases decrease, that the solubility of gases decrease with increase in temperature. Yes, that's the answer. So have that in mind, that is the answer. B, okay? Then option C, most solids decrease with an increase in temperature. That's supposed to be increase, it's typo. Most solutes decrease, nah. According to what we have here, if you increase temperature, the solubility of most solids will increase. Okay, so you have that, option C is wrong. And then most solutes, solubility of most solids is constant. Nah, that's so wrong. So the answer is B. So basically that. With this, we have come to the end of this study. Hope you learned a lot. Don't forget to solve the questions in the Efiwe app. And if you don't have it, do download it. Thank you. Welcome guys to Efiwe, Excellence Without Stress. And I remain your favorite chemistry tutor, Godson. So let's get into it. Today we're going to be discussing solubility formulas. And as we know, solubility is generally expressed as maximum amount of solute all over specific volume of solvent. So what does that simply mean? For instance now, if I happen to give you a question, and in that question I say, what is the solubility of this solution? If, for instance, I have in a cup, I have sugar, and I say that this is 1 cup of water, and then the highest amount of cubes I can put is 5 cubes. This is 1 cup. And I ask you for the solubility of this sugar in this cup. Please, your answer for solubility is going to be 5 cubes, which is the solute, divided by 1 cup, which is the solvent. Hence, my answer will be 5 cubes per cup. Another illustration. Imagine I now tell you that I can only dissolve 5 cubes in 2 cups. The implication is that my solubility will now be equals 5 cubes. Sorry, this is, wow, so much for spelling cubes. Okay, so this is going to be cubes. This is U divided by 1, no, it's 2 cups now. So which is going to make my solubility to become 2.5. What is the unit? Cube per cup. So that's that basically. So anytime you are given a question with respect to solubility, just know solute is on the top, solvent is below. And once you do that, it makes it easier for you to understand. Now, we are, however, going to be looking at different units of solubility. And the different units of solubility include mole per dm cube. Another way to express mole per dm cube is by saying molarity. But if you don't see mole per dm cube and molarity, you might see capital M. So if I say 0.5 capital M, it is simply a concentration or solubility. The next way of expressing solubility is in gram per dm cube. And then we have gram per 100 gram. Now, these are the important ones or popular ones. There is gram per 100 cm cube and gram per 1000 cm cube, and the rest of them, depending on, just note that it is simply solute on top divided by solvent, basically. And then you just consider your units. In the case where you have mole per dm cube, it means that your solute, which is mole, has to be in mole, while your solvent has to be in dm cube. Basically, that's that. Now, we go to the next one. Things to note. 1 gram of a solvent is equivalent to 1 cm cube. So what does that mean? It means that if you have in a question and they say that 1 gram of a substance, maybe they say you have 1 gram now note, they did not say 1 gram of any substance, but 1 gram of a solvent. So if I say 1 gram of water, I mean 1 cm cube of water. If the question says 20 grams of water, the question actually means 20 cm cube of water, and vice versa. Okay, then the next one is that volume of an aqueous solution is equivalent to volume of the solvent. So just in case you see a question and they don't give you the volume of the solvent, however, they told you that the volume of the solution is this, please assume that the volume of an aqueous solution is equivalent to the volume of the solvent. And an aqueous solution is simply a solution whose solvent is water. Let's get to it. The first unit we are going to consider is solubility in mole per dm cube. And there are 4 different formulas that we are going to be using to solve them. Now, I'm going to be doing the derivation so you see how we got to these things, basically. The first one is easy. Once you have a condition where your solute is in moles, if your solute is in moles and your solvent is in volume in dm cube, solubility means solute over solvent, which means the solute in moles divided by the solvent in dm cube will still give us mole per dm cube. So just have that if you have a question where the solute is in moles and solvent is in dm cube. You simply do amount of solute in moles divided by volume of solvent, and you have your solubility in mole per dm cube. The next condition is if solute is in moles and solvent is in cm cube. Okay, to help us understand this or to buttress this point, you should have come across the fact that V in dm cube is equals V in cm cube over 1000. And what does this simply mean? It implies that if solubility is going to be mole per dm cube and you have mole divided by V in dm cube, the implication is where you don't have V in dm cube, replacing it, solubility mole per dm cube will now be equals mole divided by V in cm cube over 1000. So with this said, as mathematics students, this is going to lead us to N in moles multiplied by 1000 all over V in cm cube. So that's exactly what we have here. If you look at our screen, you will notice that it says amount in mole, which is N, multiplied by 1000 divided by the volume of solvent in cm cube. So once it's cm cube, you need to multiply by 1000 to convert it basically, and that's that. And remember, dm cube to cm cube is V divided by 1000, but when you invert it, it becomes this. Okay, so note this formula. Where do you use it? Solvent in moles, solvent in cm cube, solute in moles. Then we go to the next formula. If the solute is in mass in gram and solvent is in volume in dm cube, how then do we resolve this? The formula is mass of solute in gram all over molar mass of solute multiplied by 1 over volume of solvent in dm cube. Now, remember, all these formulas is still to solve for mole per dm cube. So let's get to it. Now, the question is, you have mass, but then is there any relationship between mass and mole? Since you need mole per dm cube, how do we convert this mass to mole per dm cube? Very simple. Number of moles is equals mass over molar mass. So which means if solubility in mole per dm cube is equals number of moles divided by volume in dm cube, we'll have that replacing the number of moles with a mass equivalent is going to be mass over molar mass Instead of division, it becomes times 1 divided by V in dm cube. And that's a new formula. When you have mass and molar mass given, you're supposed to use mass over molar mass times 1 over V in dm cube to be able to resolve this, as we can see in the screen for the third scenario. Now, the fourth scenario for solubility is a scenario where you have mass in gram and then your solvent is now in cm cube. The implication is, I think you can derive this yourself, but let's do this together anyway. So doing this together, you will find out that solubility, which is supposed to be in mole per dm cube, will now be equals, where n is now going to be mass over molar mass because you have the mass, and this will be divided by, instead of having dv in dm cube, because the volume is in cm cube, we'll introduce the equivalent cm cube value, which is v in cm cube over 1000. And when we do this, the most important thing to note is conversion of this division to times. And when you do that, your formula is now going to be mass over molar mass times volume in, times 1000 all over volume in cm cube. And that's that basically. So these are simple formulas that when you solve questions, you get to learn them more. Now, we're going to try out practice questions to help us buttress this point. Okay. So they said the solubility in mole per dm cube. So note, we were asked the solubility in mole per dm cube of 20 gram of copper 2 sulfate dissolved in 100 gram of water at 180 degrees Celsius is dash. So if you look at this, the formulas for solubility in mole per dm cube are given below. But then, what is the scenario here? Our solute was given in gram. Solute is CuSO4. So which means we are either using formula 1 or we're using formula 2. Then our solvent was given in gram too. But then I told you guys, if you look at what we discussed earlier, 1 gram of a solvent is equivalent to 1 cm cube, which means when they mention 100 gram, it is equivalent to 100 cm cube. With this, I think we can solve. And what formula are we going to use? Where the solute is in gram and the solvent is in cm cube, we are going to be using the fourth scenario. So let's get to it. I will take this out and then get to the board. So we have that the mass of copper solute, copper sulfate solute, is equals 20 gram. And then we have that the volume of water solvent is equals 100 cm cube. How did we get 100 cm cube? Because 100 cm cube is equivalent to 100 grams. So just basically that. So when they give you 100 grams, it's equivalent to 100 cm cube. So it won't confuse you. And having said that, we will now get to solve. Solubility in mole per dm cube. When you have mass of solute and volume of solvent in cm cube, is expressed as we can see. Let's look at the formula one more time as mass of solute in gram divided by molar mass times 1000 all over volume in cm cube. So with that said, if we are applying that, mass over molar mass multiplied by 1000 all over volume in cm cube. So the question now is, what is the molar mass of the solute? Remember, this is the molar mass of the solute. Molar mass of CuSO4 is going to be equals 64 plus, that's copper is 64 as we saw in the question. Sulfur is 32. Oxygen is 16, but then there are 4 of them. So altogether, this is going to be 64 plus 32 plus 64. So this is 128, 130. So entirely, this is going to be 160 gram per mole. Okay, so let's get to our formula. Solubility in mole per dm cube is now going to be equals the mass, which is 20 gram, divided by the molar mass, which is 160 gram per mole, multiplied by 1000 divided by the volume in cm cube, which is 100. 0 cancels 0, 0 cancels 0. So we have 10. Okay, maybe 0 cancels 0 here. And then what do we have remaining? If 4 goes into this place, this is 4. 4 into here is 5. So 5 over 4 is going to be 1.25 mole per dm cube. So let's check our options to see if our answer is in the option. Okay, so looking at our options, we have option A 0.13 wrong, option B 0.25 wrong, option C 1.25, and that is our answer. Okay, let's try one more question to help us understand this. Now, when 50 cm cube, that should be cm cube, not cm squared, of a saturated solution of sugar of molar mass 342 gram at 40 degrees Celsius was evaporated to dryness. 34.2 grams of the solid was obtained. The solubility of sugar at that temperature is dash. So look at your units. The unit in the question is mole per dm cube, which means we should solve with mole per dm cube. So let's look at it. The dry solid was given in mass, and the mass of the dry solid is 34.2 grams, as you can see. Then what is the volume of the solvent? We are not giving the volume of the solvent, we are giving the volume of the solution. But what do we have to say? The volume of an aqueous solution is equivalent to the volume of a solvent, not mass. Volume is equivalent to the volume of the solvent. Remember, I said not mass. Specifically, volume of an aqueous solution is equivalent to the volume of the solvent, which means here that we have 50 cm cube for the solution, we are going to make it or say that it is equivalent to the volume of the solvent. So let's get to work. So with that said, our volume is in cm cube. That's the volume of the solvent is in cm cube. The amount of the solute is in gram. And with that said, which of the formulas are we going to be using? Obviously the last formula, which is solutes in gram, solvents in cm cube. And once you have that, you are going to get your answer. So looking at our values for the last time before we get to solve, we have that writing our parameters out. The mass of solute is equals 34.2 gram. The volume of solvent, they gave the volume of solution, but as I said, the volume of solution is equivalent to the volume of solvent in this case. Not the masses, I meant their volumes, because we'll come across a scenario where we need to consider the mass specifically. The volume of the solvent is 50 cm cube. And then the molar mass of solute is equals 342 gram per mole. So let's look through that again. So we have that. This is what is given for our question. And having said that, we are asked to find the solubility. Now, solubility in mole per dm cube is what we are asked to find. So we are going to use either of those four formulas, and the one that suits is mass over molar mass times 1000 all over volume in cm cube. So what's the mass? 34.2. What's the molar mass? 342 multiplied by 1000 all over the volume, which is 50. So if we take this out, this is now going to be, okay, dividing this through would be 0.1. And when 5 goes here, 1, 5 into this is 20, which means all through, this is now going to be 0.1 times 20, which is 2 mole per dm cube. Okay, so let's check our answers, our options to see if we have them there. Okay. So yes, as you can see, your answer is option A. And that is that basically about solving for solubility in mole per dm cube. The next one we're going to get into is solubility in gram per dm cube. Now, if you look at the unit, it's telling you that on top, you shouldn't have mole. What you should have on top is gram. So don't convert the gram to mole for this one. In fact, even if you have a mole and they ask you for gram per dm cube, you should convert the mole to gram before you start solving. So note, it means that the mass of the solute would be in gram, or the amount of the solute will be in gram, and it will be on top, divided by the volume of the solvent, which will be in dm cube. So just as the first scenario, if you have solutes in gram and solvent in dm cube, your solubility in gram per dm cube is simply gram divided by the dm cube solvent, basically. And then on the other hand, if your solute is in gram and your solvent is in cm cube, based on the conversion of cm cube to dm cube, the mass of the solute will be divided by the volume in cm cube, but you need to times by 1000 over 1. Let's look at the scenario or a question to understand this. If 2 grams of potassium chloride is dissolved in 500 cm cube of water, what is the solubility of the salt? Okay, so let's get to work. You will notice that we are asked if 2 grams, let's take this all out first. So 2 grams, the mass of KCl is equals 2 grams. And then you have that the volume of water, which is the solvent, is 500 cm cube. Remember, solubility in gram per dm cube. And we said if you have solubility in gram per dm cube and your solvent is in cm cube, while your solute is in gram, what is the formula to use? You will notice that the formula we are going to use is this second one, and that's that basically. So the formula we are going to be using would now be given as mass of solute divided by volume of solvent times 1000 over 1 because this is in cm cube. Okay, so getting to solve, this is now going to be 2 grams divided by 500 multiplied by 1000 over 1. So if you divide through, this is going to be 2 times this, and then our solubility in gram per dm cube will now be given as 4 grams. 4 grams per dm cube. And that's that basically about what we're discussing. So it's quite simple to solve and easy to understand. Once you have your formulas, these things are very easy to understand. Okay, finally, we are going to be talking about solubility in gram per 100 gram. Now, it is important to note that 1 cm cube is equivalent to 1 gram. So in a situation where you are asked the solubility in gram per 100 gram and you are giving your solvent in cm cube, just convert it to gram simply. Now, but before we go on, this is actually quite simple to understand. If I tell you that you should find the solubility in gram per 100 gram, you are simply looking at what amount is in 100. So if I tell you that if 2 grams is in 50, how many will be in 100? The simple answer is 4 grams per 100. If 2 grams is in 50, that means 4 grams will be in 100, and that's basic. However, if this is going to be a big problem for you, just apply this formula straight up and you get your answer. Mass of solute in gram divided by mass of solvent in gram times 100 over 1. So let's look at the question to help us buttress or understand this concept. If 4 grams of sodium chloride is dissolved in 50 cm cube of water, what is the solubility of the salt? I take it again. If 4 grams of sodium chloride is dissolved in 50 cm cube of water, what is the solubility of gram? But note, in gram per 100 gram. So it's quite simple. If 4 is in 50, the implication is that 8 should be in 100. Why? We are saying that 50 cm cube is equivalent to 50 grams. As I said, 1 cm cube is equivalent, not equal, but equivalent. You can use it in place for solvents. Okay. So, having said this, 50 cm cube, we can assume or say it is 50 grams. So, if 4 is in 50 grams, how many will be in 100? Which is 1800. However, if you want to use a formula to solve it, the formula that is going to be used is quite simple. And what is that formula? Solubility in gram per 100 gram has been expressed mathematically as mass of solute in gram divided by mass of solvent in gram multiplied by 100 over 1. Okay, so let's get to work. The mass of solute was given as 4 grams, while the mass of solvent was given as 50 cm cube, which we said is equivalent to 50 gram. You get? So with this said, applying our formula, solubility in gram per 100 gram would now be equals 4 grams divided by 50 grams times 100 over 1. Cancelling out, this is now going to give us 4 gram, sorry, this is going, yeah, so sorry about that. This is now going to be 50, 100 over 50, this is 2, and then 2 times 4 will now give us 8 grams per 100 grams. Will now give us 8 grams per 100 grams. So with this said, I presume we have come to the end of our understanding of how to solve solubility questions using the solubility formula. I remain your favorite chemistry tutor, Godson. Welcome guys to Efiwe, excellence without stress. So today we are going to be looking at another part of our study of solubility, and that is how to find the amount of crystal. Now, if the solubility of a substance is reduced, it implies that the amount that is dissolved is actually decreased. Hence, some of the solutes that were initially dissolved will have to leave the solution as crystals. We will concentrate on 2 scenarios for this crystallization, but before we get into it, let's basically do a little bit of an illustration. So if you consider your board, for instance, and you have a cup of water, remember that we said that one of the factors that causes a decrease in solubility of solids is decrease in temperature. So if, for instance, this particular solid had 5 grams inside it, and the temperature was at 25 degrees Celsius, if you tend to reduce the temperature, as we said, once you reduce the temperature, it's the same cup, but I'm just drawing it differently. So this is 10 degrees Celsius. you will notice that once you reduce the temperature, the solubility will decrease. Solubility means the amount that is inside. So let's say it decreases to let's say 3 grams. So the implication is that some of the substances that used to be inside will crystallize. And how many will crystallize? 2 grams. So what are you noticing from here? That once there is a decrease in temperature, some substances come out. And those substances that come out are referred to as crystals. Now, it is our duty to understand and show you how to find the amount of crystals for a given decrease in temperature. So let's look at this. The two scenarios we are going to be considering. The first scenario is crystallization amount from one solution. So we are dealing with one solution and there's a decrease in temperature for just one solution. How do you find the amount of crystal? And then the second scenario is where you have amount of crystal produced in one solution in relation to another solution of the same substance, basically. Okay? So getting to understand them, what are the formulas? For the amount of crystal from one solution, you simply find it by amount of crystal simply is equals the mass of solute at higher temperature minus the mass of solute at lower temperature. So just as we could see, or we can see on our screen, where we had 5 grams at a higher temperature of 25 degrees, how did we get this 2 grams here? By simply minusing the amount inside the solution at a lower temperature. So once you have that, you are asked to find the amount of crystal for just one solution. Amount of crystal, as I said, is equals mass at higher temperature, which is 5 grams, minus mass at lower temperature, which is 3 grams. Remember, it is the mass inside the solution. And when you do that minusing, you are going to have 2 grams as the amount that crystallized. So that's that basically. Now, there are questions where you might not necessarily be given the mass of the solute. You might be given the moles. So you simply do number of moles of solute at higher temperature minus the number of moles of solute at lower temperature. And that's that basically. So if, for instance, I told you that at 60 degrees, I have 7.5 moles. Then at 20 degrees, I have, sorry, this is 7, I have 5.0 moles. And then the question is, what is the amount that will crystallize when I reduce the temperature from 60 to 20? It's simple. 7.5 moles of the solute minus 5.0 moles. So higher temperature minus lower. If you do this, you are going to have 2.5 moles of crystal. So that's that basically. If you want to convert it to mass, we know now N is equals mass over molar mass. So which means mass is number of moles times molar mass. And you have your answer straight up. Very easy. Okay, so we go to the next scenario. There could be conditions where mole is not given. And instead of giving you molar mass, they give you solubility. Now, if you are giving solubility, still do solubility at higher temperature minus solubility at lower temperature. But mind you, the solubility must have the same units at both temperatures. So if I tell you or give you a question and say that in the question, the solubility of a salt is, let's say, 2 grams per 100 grams at 60 or let's say 20 degrees Celsius, and then at 15 degrees Celsius, it is equals 1.7 gram per 100 gram. And I ask you to find the amounts that crystallize for this decrease in temperature from 20 to 15. It's still the same thing. You simply do 2 grams per 100 gram minus 1.7 gram per 100 gram. Remember that what you are minusing is not the whole solution. It's simply the solutes that are inside. So you will simply say 2 grams minus 1.7 gram. And once you do that, your answer is going to be 0.3 gram. Remember, the unit of the crystal should coincide with the units of the solute, and the solute is what is on top. So that's that basically. And you have that. Once you're asked to find the amount of crystal, simply do this and you have your answer. Now, the second scenario that we're going to be considering is a conditional scenario where, okay, let's take this out, where the amount of crystal in one solution is related to the amount of crystal produced by another solution of the same substance. So there is more like a relation here. And what is the relation to solve this question? Very simple. Amount of crystal in solution 1 divided by mass of solution 1 at higher temperature is going to be equals amount of crystal in solution 2 divided by mass of solution 2 at higher temperature. So you're just looking at the relation between the both crystals in different solutions. So, but remember, those solutions must be of the same substance. So the mass of solution is equals mass of solute plus mass of solvent. So have that in mind, that if I happen to give you a question and tell you that solubility is equals 75 gram per 100 gram. Please note, solubility is solute over solvent, which means that the solubility, or if I ask you for the mass of the solution, solution is solute plus solvent. What is the solute? 75. What is the solvent? 100, which means the solution mass will be 175 grams. So this is just basic. Once you understand these concepts, it's easier to solve questions. Okay, so let's look at the formula again. I said that the formula basically is expressed as amount of crystal 1. That's amount of crystal produced by solution 1 divided by the mass of solution 1 at the higher temperature is going to be equals amount of crystal 2 divided by mass of solution 2 still at the higher temperature. So we are maintaining that their temperatures have to be equivalent to be able to solve this question. Now, there are some conditions that you must take note of to use this formula. The temperature change must be the same for both solutions. So if you are changing from 100 to 50 in solution 1, you're also going to have to change from 100 to 50 in solution 2. Then secondly is that both solutions must be of the same substance. So if this is a solution of calcium sulfate or sodium chloride, this also will be a solution of sodium chloride. Okay, let's get to solve. So the question says, the solubility of copper 2 tetraoxosulfate 6 is 75 gram per 100 gram of water at 100 degrees Celsius. Okay, let's be writing out our parameters. So at 100 degrees Celsius, solubility of the first solution 1 is 75 gram per 100 gram. Please note, solute is on top, solvent is below, as we have always mentioned. Okay, let's keep writing our parameters. So going back to the question, they now said and 25 gram in 100 gram at 30 degrees. So when you reduce it to 30 degrees, you will notice that the solubility will change to 25 grams. So at 30 degrees, this same solution 1 will have a solubility equals what? 25 gram all in 100 gram. Very good. Okay, so with this said, we continue the question. What mass of the salt would crystallize if 50 gram, now they are talking about another solution in this case. So if 50 gram of another solution of copper 2 sulfate saturated at 100, so at 100 degrees Celsius, the 50 gram is the mass of copper 2 sulfate solution saturated at 100 degrees was now cooled to 30. Remember what I said, that before we use this particular formula, you must be talking about the same substance and the temperature change is the same. So because this question happens to qualify, because temperature change is 100 to 30, 100 to 30, and then we're talking about copper 2 sulfate solutions, automatically we can use this formula. So with that said, we are going to put down the next parameter. The next parameter that we are given was the mass of the second solution. So if you look at the question, they said if 50 gram of CuSO4 solution, so notice this is not the mass of the solute or the mass of the solvent. The solution's mass for the second guy is 50 grams. So take note of that. So the mass of solution 2 is equals 50 gram. Now, and remember it was saturated at 100 degrees Celsius. So let's get to work. So the first thing we're going to do is to find the amount of crystal in solution 1. How do we find that? Amount of crystal is equals mass of solute at higher temperature minus mass of solute at lower temperature. So let's look at that. In solution 1, the mass of the solute is 75 gram. While at lower temperature, the mass of the solute is 25 gram. Hence, the mass of the substance that will crystallize in solution 1 is 50 gram. Okay, what else do we need? Mass of solution 1 at higher temperature. So what do we do to get the mass of solution 1? Mass of solution 1 at higher temperature is going to simply be solute plus solvent at higher temperature. So at higher temperature, we have that the solute is 75 while the solvent is 100, which means that this is going to be solute 75 gram plus solvent 100 gram, and that is going to be equals 175 gram. Okay, so we've gotten that. What is the next thing we need to get to solve this question? We are asked to find the amount of crystal produced in solution 2, and the mass of solution 2 was identified as 50 grams. So let's put our parameters here. So that means that we'll do amount of crystal 1, which is 50 gram, as we found here, divided by mass of solution 1, which is 175 gram, is equals amount of crystal 2 divided by the mass of solution 2, which is 50 gram. If you cross multiply, the amount of crystal 2 is going to be equals 50 multiplied by 50 divided by 175. Hence, the mass of crystal 2 would now be equals, that should be 2500 divided by 175. And I guess that should give us 14 point something. Let's just confirm. 2500 divided by 175. And you have 14.28, which is approximately going to give us. So our mass of crystal, I'm bringing it up here so that we would not need to clean the board. So up here, the mass of crystal 2 is equals 14.3 grams. And that's that basically. So let's check our options to see if that is even there. So looking up our options, this is going to be, so the solubility of copper 2 sulfate, okay, options, so that's going to be, D, that's the answer. So basically, once you are asked to find the amount of crystal, apply these principles and you get it. Now, before we end this study, every crystal that comes out of a solution, in most cases, usually comes out with a water of crystallization. So we are going to be considering water of crystallization. Now, water of crystallization is simply the number of water molecules attached to a crystallized salt. So once a salt is coming out of water and is crystallized from water, it usually has a particular number of water molecules attached to it. So you see formulas where you have, or scenarios where you have, let's say you have, taking this out, okay, back to our board, take this whole thing out. So you will see scenarios where you have, maybe they say, like your global salt, Na2SO4.10H2O. So the water of crystallization for this is 10 water molecules. You have your blue vitriol, CuSO4.5H2O, which means the water of crystallization is 5, and so on and so forth. So just note that basically when you are considering the water of crystallization, is simply the number of water molecules attached to a salt after it crystallizes. Okay, so how then do we solve for water of crystallization? Because sometimes it is important that we need to find the number of water molecules that is attached. Now, the formula to solve for the number of water molecules lost, when you heat some salts that are hydrated, they lose water. In some cases, when you tend to crystallize them, they gain water. So we're looking at the number of water molecules that they lost or they added by heating or by crystallizing. You get? So it's very basic. How to solve this? Given mass of water lost or added all over given mass of hydrated salt will be equals molar mass of water times X all over molar mass of hydrated salt. So it's just mass of water, mass of salt, mass of water, mass of salt. However, notice here, given mass, molar mass, molar mass. And then we have to note that there is X here. And what is this X? X is simply the number of water molecules lost. Now, it's also important that you note that when I'm using hydrated, I use hydrated for both sides. But when I'm using anhydrous, I use anhydrous for both sides. So given mass of water lost or added over given mass of anhydrous will be equals molar mass of water times X divided by molar mass of anhydrous. The emphasis is how do we find X. So remember that I said X is simply the number of water molecules lost. But then, if the salt is heated to a constant mass or is heated till it becomes anhydrous, the implication is that the number of water molecules lost is equal to its water of crystallization. So just have that in mind, that if they tell you that it was heated to constant mass, that water that was lost is the total number of water molecules there, which gives you the water of crystallization. Heated to a constant mass means that every single water molecule has been evaporated. Okay. Now, A hydrated salt is made up of the water of crystallization plus anhydrous salt mass. So which means if you are looking for water, you simply do hydrated salt. It should be hydrated, not hydrated, minus anhydrous salt is a typo. Okay, so let's solve a question to help us understand this. Now, before we even solve a question, note that you are likely to be given the molar mass of your hydrated salt. But if you're not giving your molar mass of hydrated salt and you're giving that of anhydrous, it means that you're going to use the anhydrous formula. So it's just that basically. So in some cases, you need to use the hydrated formula. In some cases, you need to use the anhydrous formula. Whichever the case is, just look at it, understand it, and apply your formula. So let's analyze this. We are told that 2.5 gram of hydrated barium salt gave on heating 2.13 gram of anhydrous salt. So let's be putting down I like putting down my values straight up. So 2.5 grams of hydrated. So hydrated means that it has water of crystallization, and we don't know that water of crystallization. So a barium salt, let's call it barium X. Okay. Let's not use X because X is going to work as. So let's call it barium B. Then it is attached to X water of crystallization. So they said it was heated to a constant mass until it became anhydrous. Remember I told you constant mass means that it is now anhydrous. And that gave us 2.13 gram of BAB. This time around, constant mass means all the water has been lost. So no water of crystallization. Now let's continue the question. As I said, I like taking my questions in steps. It helps me understand better. So given the relative molecular mass of the anhydrous salt is 208. So we are given 208. Let's write that down. So the molar mass of the anhydrous salt, which we say is now BAB, is equals 208 gram per mole. Okay, if we are using molar mass, but if it's relative molecular mass, then yeah, no unit. Now let's continue. The number of molecules of water of crystallization of barium is that. So we're looking for X. So looking at this, if you notice, we have the molar mass of the anhydrous salt, which means instead of using the first formula for hydrated, we are going to use the second formula. If we had the molar mass of the hydrated, we'll use this. So just note, whichever molar mass you can find or is given is what will determine the formula you are going to use. So we're going to use the second one because we have the molar mass of the anhydrous. So let's get to work. Now, solving this question is going to be a very easy thing. So let's get to. So that's going to be given mass of water divided by given mass of anhydrous salt will be equals, molar mass of water is 18, so we can just write 18x. You can find that out. H is 1 times 2, which is 2 plus 16, that's 18. So we can just write 18x. Then the molar mass of anhydrous salt. So notice anhydrous. Molar mass, given mass. So let's first find the given mass of water. So I mentioned that the given mass of water is given as hydrated salt minus anhydrous salt. So that's going to be 2.5 minus 2.13. And if you do that, that is going to be numerically equivalent to, okay, so 2.5 minus 2.13, that's going to give us 0.37. So that's that basically 0.37 gram. Okay, so we've gotten the given mass of water. So let's now put our values. Given mass of water is 0.37 gram. The given mass of the anhydrous salt, according to the question, is 2.13 gram. And this is going to be 18 multiplied by X divided by the molar mass of the anhydrous salt, which we got to be 208. Or yeah, was given in the question as 208. If you cross multiply, this is now going to be X equals 208 times 0.37 grams divided by 18 times 2.13 grams. That's like making X operator formula. I did that straight up. So you can do that. So you have 0.37 multiplied by 208 divided by your 18 multiplied by 2.13. And when you do that, your answer is going to be 2.0007. So X is approximately 2. So which means because it was heated to a constant mass, as we noticed, we said that if the salt is heated to a constant mass or heated till it becomes anhydrous, then whatever number of water molecules that is lost is equivalent to the water of crystallization. Remember, this formula is to find the number of water molecules lost, which is X. But then, if you are able to find the number of water molecules lost and it was heated to a constant mass, it means that that water molecule loss is the same thing as its water of crystallization. Hence, we have that the answer is 2. With this, I presume you have understood how to solve questions with respect to water of crystallization and how to find the amount of crystal. I remain your favorite chemistry tutor, Godson. Welcome guys to Efiwe Excellence Without Stress, and this is the final part of the study on solubility, and it's known as solubility product. Solubility product is simply defined as the equilibrium constant for a dissolution process. So just have that in mind, that once you are dealing with the equilibrium constant for a dissolution process, what you are describing is solubility product. For you to be able to understand it, you must understand that to find the concentration of ion, it is equals the concentration or solubility of the dissolved salt or substance multiplied by the number of moles of ions. Now let's get to derive our formulas. Now, if you are dealing with solubility product, as we said, for every reaction that is a dissolution reaction, let's say we have C, D. Let's say we have CX, DY, and it is a solid and is dissolved to give your aqueous solution of C, which is the positive ion, and your aqueous solution of D, which is the negative ion. So the number of moles of C in this case is X, while that of D is Y. Remember that this reaction is supposed to be reversible. Equilibrium constant is the active mass of the product divided by the active mass of the reactant. So what is an active mass? An active mass is simply the concentration of that substance raised to the power of its coefficient in the balanced equation. So if we are looking for the active mass of C, the active mass of C is going to be concentration of C raised to power X. The active mass of D is going to be concentration of D raised to power Y. So just have that in mind. Then finally, the active mass of CX dy is going to be concentration of CX dy raised to power 1, because there's just one mole. But then it's important for you to note that the active mass of a solid is equals 1, so we don't need to use this. Hence, if we are asked to find the solubility product, which is the equilibrium constant for a dissolution process, is going to be the equilibrium constant, which is active mass of product, which is concentration of C positive raised to power X multiplied by the concentration of D negative raised to power Y, all divided by the active mass of the reactant. But because our reactant is a solid, the value is equals 1. Hence, our solubility product is simply going to be the concentration of the cation raised to the power of the number of moles of the cation multiplied by the concentration of the anion raised to the power of the number of moles of the anion. So we have this basically as the first formula for resolving solubility products. Now mind you, X is equals number of moles of cation, YY is equals number of moles of anion. So this is the first formula we are going to be deriving, but then this formula can actually be made simpler such that you can relate solubility directly to solubility products. And how do we do that? Very simple. Apply mathematics. So our understanding of mathematics is going to help us solve this, but we must first note that solubility product, as I said, is simply the active masses of the cations multiplied by the active mass of the anion. With this said, we move ahead. Remember that in our slide, if you look at the slide, the point that was made in the slide is that the concentration of any ion is simply equals the concentration of dissolved salt or solubility, note, or solubility of dissolved salt or substance multiplied by the number of moles of the ion. And what is this trying to denote, or what is this trying to tell us? That anytime we are looking for concentration, note, the square bracket indicates concentration. So if I'm looking for the concentration of C+, it is going to give me, or it is going to be expressed as the solubility of the salt that produced it. Remember that it was CX dy that dissolved to produce C plus, that's xc plus yd minus. So note that it is going to be equal the solubility or concentration of that salt, so solubility of salt, multiplied by the number of moles of C. What is the number of moles of C in the balance equation? X. Which means that if I'm looking for the concentration of D, it is going to be the solubility of the salt that produced D multiplied by the number of moles of D, and that is Y. If we infuse this into this equation, we are going to have that solubility product will now be equals, for C raised to power x is going to be, concentration of C raised to power x is now going to be, remember that the concentration of C is S times x, so this will be S times x all raised to power x, multiplied by, in the case of D, is going to be S times y all raised to power y. Mathematics will now tell us that if we happen to apply indices, this is going to be S raised to power x times x raised to power x times s raised to power y times y raised to power y. Collecting like terms, our k of s of p is going to be equals s raised to power x times s raised to power y times x raised to power x times y raised to power y. So finally we'll have that the solubility product is going to be solubility of the salt raised to power the sum of the number of moles of the cation and anion multiplied by x raised to power x times y raised to power y. So this is our second formula for solving solubility product. So when you want to relate solubility product to solubility directly, you use this formula. Note, x is number of moles of cation, y is number of moles of anion, k of s of p is solubility product, and then s is the solubility or concentration of the dissolved salt. Having said this, we will now get to a final relation. If I want to now find solubility when I'm giving solubility product, I simply make it subject of formula. From this formula, it is now going to be, making solubility the subject of formula, will have s raised to power x plus y is equals k of s of p divided by x raised to power x times y raised to power y. Hence, the solubility is going to be a root of x plus y of k of s of p divided by x raised to power x times y raised to power y. So we now have our new formulas and we're going to solve some questions. So let's try out these questions to help us understand this. A saturated solution of AgCl was found to have a concentration of 1.30 times 10 raised to power minus 5. So we are given the concentration. As I said, in this case you can use concentration in place of solubility. The solubility product of AgCl is dash. You are asked to find the solubility product when you are given solubility. So let's get to solve that. First off, let's take this off. So writing out our parameters is one essential thing I like to do. So putting this down, first off, you put down your reaction. AgCl solid, if it is going to dissolve in water, will give Ag plus Cl minus, aqueous solutions. How many Ags do I have? I have 1, so my x is going to be 1. How many Cls do I have? I have 1, so my y is going to be 1. So writing them out, the number of moles of the cation is 1, the number of moles of the anions is 1. Then was I given the solubility of the dissolved salt? Yes. The concentration of the dissolved salt was given as 1.303 times 10 raised to power minus 5. And note that we are asked to find the solubility product. So with that said, we are going to have that this is 1.30 times 10 raised to power minus 5 mole per dm cube, and then we are asked to find solubility product. Is there any formula that relates solubility product to solubility directly? Yes. And what is the formula? Solubility product is equals s raised to power x plus y, x raised to power x times y raised to power y. So let's get to work, which means that the solubility product is going to be equals s. What is our s in this case? 1.303 times 10 raised to power minus 5 is the s, raised to the power of x plus y, which is 1 plus 1, multiplied by 1 raised to power 1 times 1 raised to power 1. If we resolve all this, what we are going to have here is 1.303 times 10 raised to power minus 5 all raised to power 2. With this said, our final answer is going to be 1.69 times 10 raised to power minus 10. And that is going to be the solubility product. So let's check if our answer is in the option. And you have that our answer is option C. One more question and we call it off. The solubility product of CuIO32 is 1.08 times 10 raised to power minus 7. Assuming that neither ions react appreciably with water to form H plus and OH, the implication is that there is no interaction with these ions, so ignore these ions. What is the solubility of the salt? So let's get to solve this question quite easily. Now, the first thing we are going to do is, what were we given? Solubility product, and you are asked to find solubility. How do you relate or find solubility when you are given solubility product? Very simple. From the formula we derived, we have that solubility is equals root x plus y of k of s of p, which is solubility product, divided by x raised to power x times y raised to power y, which means solubility is going to be equals, okay, let's first, we don't know what the solubility is. Our solubility product was given as 1.08 times 10 raised to power minus 7, and we have that our okay, let's write our reaction. So CuIO3 bracket 2, when it is broken down, will give Cu2 plus IO3 minus. How many Cu do I have? I have just one. How many IO3s do I have? I have 2, so I'm multiplying it here. So multiplying it means that the x, which is number of moles of cation, is 1, while the y, which is number of moles of anion, will now be 2. Solving this, we apply it to this formula and get our answer. The solubility is now going to be given as bracket x, which is 1, plus y, which is 2, root. So 1 plus 2 will give us cube root of k of s of p, which is 1.08 times 10 raised to power minus 7, divided by 1 raised to power 1 times 2 raised to power 2. If we do this, our solubility is going to be equals cube root of, well, let's convert this to 108 times 10 raised to power minus 9, so we can do the cube root easily, and then we have that this is going to be divided by 1 raised to power 1 is 1 times 2 raised to power 2, which is 4, so it's going to give us 4. If you go through with this should give us 27. Yes, and with this we now have a perfect cube. So we'll have that s is going to be the cube root of 27 times 10 raised to power minus 9. And if you do this, cube root of 27 is 3, and cube root of this is going to be times 10 raised to power minus 3. And that is going to be our answer. The solubility is 3 times 10 raised to power minus 3 mole per dm cube. With this, I presume you've understood this. Thank you very much for joining us. Don't forget to solve the questions on the Efiwe app, and if you don't have it, do download it.